Hey guys, welcome to our first video of integration, area under a curve, day one. In this lesson, we're going to be approximating area under the curve using what is called Riemann sums. Before we begin, let me go ahead and ask you guys a quick question that we can understand why we are doing this. A train is traveling 60 miles per hour for 2 hours straight. How far does the train travel in 2 hours? Well, you guys would be able to answer this using physics. So, you know that in physics, v, velocity is distance over time. And to find distance, you would manipulate this equation, and so that you get time times velocity is equal to distance. And then you would go ahead and plug in 60 miles per hour times 2 hours. Hours cancel, and you get 120 miles. Now, let me go ahead and show you guys the answer using a graphical approach instead of this traditional physics approach. So let me go ahead and do this. Let's graph the train's velocity. This is going to be v for velocity, t for time. This is going to be your vt graph. Now, your vt graph. Your train is traveling 60 miles per hour for 2 hours straight. It's not getting faster, it's not getting slower. So for 2 hours straight, the train travels 60 miles per hour. So here's hour number one and hour number two. What if I take the area underneath the train's velocity graph? I form a rectangle. What is the area of a rectangle? It's your base times height. What is the base? The base is 2 hours. The height in this graph is 60. If I take 60 times 2, I get 120, and I would have to answer in meters because I am looking for how far the train is traveling, which is distance. Coincidence? No. This is just one of the secrets of mathematics that has been revealed to us a long time ago. So we can find the area underneath the velocity. So if you remember your PVA, position, velocity, acceleration, you guys remember that taking the derivative with respect to time, you go to the right. The derivative position, velocity, acceleration. And then taking the integral, this elongated S symbol, which is what you're going to be learning later on, which is the same thing as area under the curve. Taking the area under acceleration will give you velocity. Taking the area under velocity will give you position. Now you're going backwards. Okay, and that is one of the reasons why we study area under the curve integration. So let's go ahead and begin with our lesson for today. A car is traveling so that its speed is never decreasing during a 12-second period. The speed at various moments in time is listed in the table below. So let's go ahead and do letter A. Sketch a possible graph for this function. Here are all the times. Let's go ahead and draw a graph of this. Here's 0, 12, 6, 3, and 9. This is going to be 65. I'm going to pretend this is 30. So the first points we have are 0, 30, 3, 37, 6, 45, 9, 54, and 12, 65. And because this part says it's never decreasing, that means we could possibly have a concave up curve. Now that was a terrible curve, but pretend it's concave up. Okay. Letter B, estimate the distance traveled by the car during the 12 seconds by finding the areas of 4 rectangles drawn at the heights of the left endpoints. This is called left Riemann sum. So how do we draw the 4 rectangles using left Riemann sum? Let's start with the first point, 0. Draw your height of the rectangle up, then go to the right where 3 would be, and then go straight down. And then starting again from 3, this is going to be your left part of a new rectangle. Go up, right, down, up, right, down. And then finally, the last rectangle. This is called left Riemann sum because we start from the left and that's how we draw our rectangles. What is the height at 0? This is 30. What is the height at 3? This is 37. Let me use another color for this. So let me use black instead. 37. The height at 6 is 45. The height at 59 is 54. And finally, 65. The height for this long black line here. Okay, so let's go ahead and use left Riemann sum. So we're only interested in these 4 rectangles here. This one, this one, this one, and this one. So what are the bases of each of these rectangles? As you notice, they all go by 3. So the base is 3, 3, 3, and 3. So the area or the distance that we're trying to find is approximately the base times the height, which is 3 times 30 plus 3 times 37 plus 3 times 45, and the last rectangle is 3 times 54. Now notice we did not use 65. Okay, we're using the left Riemann sum, so we only needed 4 heights because 30 is our first height. 30, 37, 45, 54 are our first 4 heights. So whenever you use left Riemann sum, you're only using the first points, omitting the last. Let's go back to the answer here in the bottom. What do you notice? What do you notice that all these numbers have in common? They all have a times 3, so you can factor out a 3, 30 plus 37 plus 45 plus 54. And if I add up all those numbers, I should get 3 times 166. And then I would multiply times 3, and I get 498 feet, since I'm finding distance. So this is the answer for left Riemann sum. Now let's look at the follow-up question behind that. Is this an over or under approximation? What do you guys think? If I highlight all this area of the rectangle, is it an over approximation of what the true area would be, or is it an over approximation? And if you notice, there's still some area in between here. So that means that we actually have an under approximation. Let's go ahead and go to letter C. Okay, letter C. So in letter C, we have estimate the distance of traveled by the car in 12 seconds by finding the areas of 4 rectangles drawn at the right endpoint. So let's draw this differently now. Now we're going to be focusing on the right endpoint. So we're going to start from the right and then to the left. Right to the left. Right to the left, and the final rectangle. Now for right Riemann sum, we're using the right endpoints. So we're going to be using 37, 45, 54, and 65. So we're not going to be doing the first 4, we're going to be doing the last 4. So for right Riemann sum, we omit the first and then do the last. For left Riemann sum was the other way around. We would omit the last and compute the first. So let's go ahead and compute the area. Area, which is our distance, is approximately, and I'm going to skip a step here. I'm already going to add all the heights. So it's going to be 37, 45, 54, 65. And when I do that, I get 3 times 201, which is 603 feet. That is about a 205 feet difference. So Let's go ahead and look at the follow-up question for this. Is it an over or under approximation? And you guys are probably already thinking it's over. I have a lot of area above the actual true area of what this graph could have. So this is an over approximation. And in the next video, I'll show you guys two more methods of finding areas in the curve, and then that'll be it for this lesson. See you then.